And let's proceed to Mohan from Beijing Institute of Technology. You will have 10 minutes to present your study. Mohan, are you here?
Yes, I'm here.
Okay.
Hello.
Can you share the screen with us?
Oh yeah, sure.
If there is any missing speakers and you are allocated to this session, but I do not know, and let me know through the chat box. And at the moment, I have 3 remaining speakers, 2 from Beijing Institute of Technology, and 1 is another speaker just communicated with me. Okay, go ahead, Mohan.
Okay. Hello, everyone. Good afternoon. I'm Mohan. I'm from Beijing Institute of Technology. I'm now a doctoral student, and it's my honor to give this speech and discuss with you about my research. And the topic is MPC-based lateral control strategy for bus path following control. And the speech is carried out in 4 parts. So firstly, the introduction of research topic. The road of buses is relatively fixed compared with private cars, so this provides a suitable scenario for path following control. And the purpose of path following control is to control the steering system of the vehicle to track the desired trajectory curve while satisfying performances such as safety and energy consumption. An MPC method is good in adaptability and robustness. The inputs of control strategy are the vehicle state variables, steering angle, and objective path. The output is front wheel angle, which is the control variable. And the purpose of the control strategy is to follow the target path with the smallest control variable. And the variable definitions are listed in this table. The state variables are acquired from GPS, the target path is fixed, and the control variable is recorded by control strategy. We use kinematic model as the predictive model. According to the variable definitions, the predictive model is expressed as the formula below. So these are the formulas. And the formula is linearized using Taylor series expansion algorithm. Then the formula is discretized using Euler's method. We assume that at each moment, the predictive model keeps the same until the next moment. So we have this assumption. Thus, we get the linearized and discretized kinematic vehicle model to predict the vehicle states. We define the objective function as the combination of both tracking error and the control variable to achieve the control target by the smallest action. So we can see that U is the control variable, and Y, it means the tracking error between our real path and the target path. And the constraint is the change rate of control variable due to the mechanical limits. And we use predictive model. In predictive model, a curve preview method is used, as can be seen in this figure. Once the preview point is determined, that is point M, it is regarded as a fixed point on the rigid body of the vehicle. And we use QP OASIS to solve the following form of quadratic programming problems. And simulations based on MATLAB, Simulink, and TruckMaker platform is conducted. The vehicle model in TruckMaker is close to the real vehicle. Thus, the simulation results are used to study the effects of the change of parameters. Here's the structure of simulation platform. The lateral control strategy is wrapped in S function. Vehicle tests is conducted to verify the effectiveness and real-time performance of the control strategy. And this is the structure of the vehicle tests. Two scenarios, including straight line and right angle turn road, are designed. We assume that the friction coefficient of the road is 0.8. Different velocities are simulated in the simulation platform and vehicle tests. The tracking errors for each condition are listed in this table, and we can see that the tracking error is lower than 10 centimeters in all conditions. This is the results for the simulation platform. And take the 20-meter radius right angle turn with the velocity of 10 kilometers per hour as an example. The tracking error of different friction coefficient is shown in the left figure, and the tracking result is shown in the right figure. We can see that the maximum tracking error is about 0.1 meters. For real vehicle tests, in straight road conditions, the tracking error grows with the increase of velocity, as can be seen in the left figure. The tracking results of right angle turn with velocity of 15 kilometers per hour is shown in the right figure. The target path is not smooth. The red line is the target path because there's some noises in the signal. However, the vehicle can follow the path smoothly despite of the noises. The proposed vehicle lateral control strategy can realize a reliable and stable tracking action. Preview method can help reduce the tracking error. And in real vehicle tests, due to the noises in target path, the tracking error will reach a higher value than that in simulations. The real-time performance can be verified according to the real vehicle tests. In conclusion, an MPC-based vehicle lateral control strategy is proposed in this study. The prediction step of MPC needs to be reduced with the growth of vehicle velocity, and the reliability and real-time performance is verified. The tracking error is within 15 centimeters in simulation platforms. And here are the references. Thank you for listening.
Thank you, Mohan, and excellent presentation and perfect timing. And if for the audience, if you have any questions, want to communicate with Mohan, and you can communicate through the chat box. So now we proceed to the second speaker from Beijing Institute of Technology.